Alright, for this problem, we have a fire alarm in a firehouse going out, so it's sending out sound waves in all directions. And when this happens, we have three different observers here. We have a firefighter that starts running towards the firehouse. Okay, so there's our firefighter running towards the firehouse. We have a dog that's running away from the firehouse. Alright, so there's our dog running away from the firehouse. And we have a person here just standing there at rest. And so we want to rank from least to greatest the period of the sound wave heard by each person. So two things we want to keep in mind. The first is with the Doppler effect, we know that frequency increases with motion towards and decreases with motion away. All right, so that's the first thing that we want to keep in mind. And the second is that frequency and period are inversely related, okay? We want to ultimately rank the period, but let's first figure out which one has the greatest frequency. So, the firefighter moving towards, that's going to lead to an increase in the frequency. And so that means that the firefighter is going to hear the greatest frequency of the sound wave, and so that means it's going to be the smallest period. Okay, because the firefighter is moving towards, that's going to increase its frequency. The person doesn't move at all, and so they're going to hear the true sound, so they're going to hear a lower frequency than the firefighter, which means they're going to have a greater period for the sound wave that they hear. And then the dog moving away is going to hear the lowest frequency, okay, because that motion away decreases the frequency, and so that means the dog's going to hear a sound wave with the greatest period. All right, and so that's going to be your ranking there. Alright, for this problem, we have a red-bearded tuba player running down the hallway at 1/10 the speed of sound. Alright, so there's a red beard there. I'm going at 1/10 the speed of sound, so I'm just going to say V is the speed of sound, so this is going to be V over 10. I want to calculate the frequency heard by a stationary observer when he is running towards him. Alright, so it made it sound like that. And then part B, when he is running away from him. Alright, so let's start with part A, where we, of course, are going to set up our Doppler effect. Frequency observed is the frequency of the source, times V plus or minus VO over V plus or minus VS. In this case, we have no velocity for our observer. Our observer is stationary, so the frequency observed is just going to be the frequency emitted, which is F, times V, our speed of sound, over V, our speed of sound once again, and then the velocity of the source, which is V over 10. So for this first one, we just need to figure out whether it should be a plus or minus. Since the red-bearded tuba player is moving towards the stationary observer, that's going to decrease the frequency, so we're going to subtract on the bottom here. And so our frequency observed is going to be F times V over 9/10 V. Okay, our V's cancel out. And what we're left with is frequency observed is F times 1 over 9/10, which is really 10/9 times F. So that ends up being our final answer. For part B, we're going to start with that same equation for the Doppler effect. Our observer still is not moving, it's just that our source is now going away. So the only thing that's going to change here is rather than subtracting that V over 10 on the bottom, we're going to add that V over 10 on the bottom. We're going to add the velocity of our source because him moving away from the observer is going to decrease the frequency, causing us to divide by a bigger number. So our frequency observed is going to be F times V over 11/10 V, adding in that. All right, we cancel out our V's just like we did before, and so it becomes F times 1 over 11/10, and we get rid of that double fraction by flipping it, and so our frequency observed ends up being 10 over 11 times F. Alright, for this problem, we have two girls that are driving towards each other. Alright, so we'll say the velocity of the girls is just VG, we'll call it. Okay, at really, really fast speeds, one girl hits her horn emitting a sound, alright, that is heard by the other girl at twice the frequency as if they were at rest. So we're going to set up our Doppler effect. The frequency observed is the frequency of the source times V plus or minus VO over V plus or minus Vs. Both objects are moving in this case, so we're going to have both a VO and a VS. We also know that the frequency observed is twice the frequency as if they were at rest. So I'm going to say that this frequency observed is 2 times the frequency of the source. And then we just have frequency of the source times V, and then I'll figure out the plus or minus in a second, but it's going to be Vg, the velocity of the girls, and then V and Vg once again. So let's take this one at a time. The observer in this case, this car here is moving towards the source. That's going to lead to an increase in the frequency, and that means that I'm going to have a bigger number on top. So I'm going to say plus Vg on the top. For the frequency or the velocity of the source is moving towards the observer. That also increases the frequency. It's a double effect here because both are moving. And so I want to divide by a smaller number, and so it's going to be minus Vg on the bottom. These FS's can cancel out, and what I'm going to do is I'm going to multiply both sides by V minus Vg to get rid of that part on the bottom there. And so what I get is 2 times V minus Vg equals V plus Vg. I can distribute here, 2V minus 2Vg equals V plus Vg, and we'll go ahead and group all the Vg's together and solve. So I'm going to add the 2Vg to that side to make it 3Vg, and subtract the V from the left side to get just regular old V. And so I find that the velocity of the girls is V over 3, or 1/3 the speed of sound. This question asks, why do notes played on a musical instrument sound more pleasant than simple notes played on a tuning fork? And the answer here really relies on one thing and one thing only, and that is harmonics. The key is that when we play a note on a musical instrument, there are multiple harmonics that are generated from that same note, multiple frequencies, and those harmonics add together, okay, to produce a more complex and richer wave, and that's really the key. When dealing with a tuning fork, though, it's only a single frequency being produced. A tuning fork is designed to only produce that single, simple wave. Alright, for this one, we have a string on a violin where both ends are fixed, has a length of L, and when the full length of this string is used, the third harmonic has a frequency of F. We first want to find the velocity of the waves on the string. So first I'm going to start with my equation for 2 fixed ends, m lambda over 2 is equal to my length. We know that we're talking about the third harmonic here, so that means that m is equal to 3. And so my wavelength here is going to be 2/3 L. All right. And I know that the frequency of that wavelength is F, so I can say velocity is wavelength times frequency. So my velocity here is going to be 2/3 L times the frequency, or just 2LF over 3. For B, we want to know about the fundamental frequency that occurs when m is 1. So I'm going to set up my equation once again for 2 fixed ends, or 2 ends that behave the same, really, I should say. So L is equal to 1 times lambda over 2, which means the wavelength of my fundamental frequency is just 2L. And I can use that combined with the velocity that I know here to solve for that fundamental frequency. So I can say velocity is wavelength times frequency. I know my velocity is 2LF over 3, and my wavelength here is 2L. And so I can solve for my frequency here, my fundamental frequency, which I'll call F prime, not to be confused with this F here, which was the frequency of the third harmonic. I can cancel out the 2 L's on both sides, and I find that my frequency for the fundamental frequency is just F over 3, 1/3 of that frequency for the third harmonic. The last part asks, how could you change the fundamental frequency? The key really is to change the medium here. Okay, and so the easiest way to do that, especially with the violin, would be to change the tension, and that's exactly how a violin gets tuned. That's how we make that fundamental frequency have whatever the proper note should be. Okay, by changing that tension, we can tune it to the right frequency, and then everything just follows from there. For this next one, we have an organ pipe, which is open-closed, plays a note with a frequency of F. The speed of sound here is going to be given by V, and we want to know the length of the pipe. First thing I'm going to do is say V equals lambda times F, and I'm going to solve for my wavelength here, and that's going to help me eventually find the length of the pipe. So my wavelength is just going to be V divided by F. Now that I have that, I can say that the length of the pipe is m lambda over 4. That's what we do when it's open-closed. My m in this case is going to be 1 because the frequency we hear is the fundamental frequency. Okay, so if you hear a note, that note is the fundamental frequency. Those harmonics just add complexity. So I can plug in the things I know here. I'm solving for L. My m is going to be 1. Wavelength is V over F all over 4. And then I'm just going to simplify that to find that my length here is just going to be V over 4F. For the second part, we want to know what would happen if the pipe were filled with helium, where the speed of sound is faster than what it is in air. Would this frequency increase, decrease, or remain the same? The key thing to look at here really is the fact that the length and the wavelength are directly proportional to each other, and the length of this pipe is not changing, so therefore the wavelength is not changing either. And in that case, all we need to look at is our equation that relates velocity and frequency, and we can clearly see that if our velocity increases, our frequency must also increase because they are directly proportional to each other. And this matches up with what our experience is with helium. We know that if someone inhales helium, their voice gets higher pitch, higher frequency. So that makes sense with what we know about helium.